Hello everyone, my name is Hayman Aziz. This video on finite shapes with infinite boundary is the continuation of a number of videos related to the image of infinity in geometry. The starting point here is as the following. For example, we assume, just for simplicity, like 2D shapes and 3D shapes, there are billions or maybe infinite number of different possible shapes in either of them. So it means it may not be very easy to assume or imagine that I have got a 2D shape in which it has a finite area but infinite boundary. Maybe we can imagine easily here if the size or maybe the area of this shape is infinite, its perimeter is also infinite. But we cannot easily assume in our mind here if the area is finite, the boundary is infinite. The same thing here for example, 3D, the same thing. For example, we cannot imagine easily here you have got a 3D shape in which it has got a finite volume but infinite surface. Okay, so now the next step here is there are usually two main properties of any shapes. It means there are many properties obviously, but these two main properties are the ones in which we studied in this video. For example, if I take a 1D shape, in 1D shape, I have got the length, usually the length expands itself on a 1D or one-dimensional space. But the two ends, in which you have got two ends, okay, this is the boundary, or maybe this is, we can't call it perimeter, obviously. This is the ends, and the ends are in 0 dimension. You know that imagining 0 dimension may not be easy, but at least if, for example, we assume this is 1 dimension, or this is lowered by 1, then it can be possible, at least theoretically, that the line has infinite length, but still with two ends. So it means the situation with 1D is different here. It can be possible the length of this is infinite, but it has got just only two ends, which is finite. It may not be possible. Let us say you have got a line or maybe a 1D shape, but it has got a finite length but infinite boundary, infinite number of ends. Now 2D shape. 2D shape, those properties are firstly the area. The area here is within 2D. And secondly, here is the circumference or maybe the boundary, which is in 1D. So again, here we have got the same situation, 2D, 1D, 1D, 0, and so on. Then, in basics, we have learned that it can be possible, for example, here, for shapes, they have got the same area but different perimeters, or maybe different areas but the same perimeter. These are quite common. But usually we as human, our intuition and sense always tell that whenever the area of the shape is finite, its perimeter must always be finite. Or if, for example, here the perimeter is finite, its area must always be finite. Okay, at least, for example, here, these facts we already know. But now the question is it possible for a shape to have a finite area but infinite perimeter? Or is it possible for a shape to have a finite perimeter and infinite area? The main focus of this video is the first one, not the second one. We give the reason why. Now, we need to understand some basics of calculus For example, here, this is something in which we have learned that in identifying or maybe defining area under the curve between 2 points, or of a function between 2 points, which is given by this integration. The length of, for example, the curve or the function between these 2 points is also defined by those. I'm not going to show the proof or maybe verification of these two formulae because if you look at most of calculus textbooks, you see the derivation of those two formulae. But here we just assume it as a fact. Now, this is a simple example. This simple example here is f of x is equal to 1 over x. And this function we assume is defined in this domain between 1 to infinity. Now, if I calculate the area comes out to be infinite. If I calculate the perimeter, although already this side is infinite, but just maybe for an extra demonstration, the length of this function can also be found through this integration. Then this integration may be solved by analytical way, but we are not spending time on that one. We just simply expand it by binomial expansion here because this quantity is less than 0, and then this can also be demonstrated as is infinite. So perhaps nothing is strange here because you have got this area is infinite and the size or maybe the boundary, which is the perimeter, is infinite. There is nothing strange here. But now the strange thing is here. If I have got a different function, this time here 1 over x squared, in this 1 over x squared, if I calculate the area comes out to be equal to a finite value. In the same way as we had previously here, if I work out the perimeter, which is this length plus this length plus this end length is 0 already, and this length. So if I add all of those, this is the perimeter of the shape. And then even if I do not calculate the integration from 1 to infinity, which is one side of my shape, is enough to tell that the perimeter is infinite. So we have got a finite area, but infinite perimeter. But now the question is it possible for a shape to have an infinite area with finite perimeter? The answer is not. Now, 3D shape. In the case of 3D shape, the two properties are volume, in which it is this content in which you have, which covers the 3D, and the surface area. The surface area of this shape here is a two-dimensional world. And the same thing as we had before, it can be possible, for example, for the same volume but different surface area, but different shapes, obviously, or maybe the same surface area but different volumes, again, different shapes. So in the same way as we had in 2D, our intuition normally tells that if you have got a finite volume, you must always have got a finite surface area, and the other way, or maybe vice versa. But we will demonstrate in this video here that it can be possible you have got a finite volume, but infinite surface area. Now, we need a little bit understanding in rotation of, for example, functions. So this is helping us to produce some shapes, some 3D geometrical shapes in which they are part of the discussion in which we are aiming here in this video. If, for example, I have got a function, and if this function is rotated about the x-axis, then if I calculate the volume, this is the formula. Again, here, this formula can be found in most of the textbooks in calculus. The total surface area, I mean the sides, is equal to that, but obviously here, if you add the two surface area of the two sides. This is simply modified by this part, in which certainly is equal to pi f of a the whole squared, and then plus pi f of b the whole squared. So the main point is not these two, because always whatever happened, these two are quite small and constant here. The main part in which is playing role in this discussion is this integration, by the way. An example. So this is an example here, e to power minus x, and this e to power minus x, if you calculate it, certainly here the area comes out to be finite. And then if you calculate the surface area, this is just changing variable here for this integration, because this integration cannot be solved easily. But if you do a number of variable changes, then you can simplify it into a simpler integration, and then if you substitute, then you will get a finite value. So it means this may be understandable, because you have got a finite area and finite surface area and finite volume. Now another function. So now f of x is equal to 1 over x. If you use the rule in which we had for the volume, this comes out to be pi, which is finite. And if I work out the surface area plus pi is the surface area for the circle, because if this is equal to 1, the radius is equal to 1. And the other end, because this is infinity here, then it is automatically 0. Then if you calculate this integration, but this integration is highly nonlinear, then it means applying normal rules of integration may not be very easy, but still it can be solved analytically here. But I'm not going via that route, because understanding it for our purpose through the expansion in binomial maybe is easier, much more easier. The reason is because 1 over x to power 4 is already smaller than 1. Then it means justifying this expansion is easy. But then once you expand it here, the integration of 1 over x is ln. This is the main part here, which is playing role, because the others are just normal constants. I'm not too worried about those. But ln x, if you take the limit at x infinity, this is equal to infinity. So it means this is one of the examples in which it has got a finite volume but infinite surface area. There is a little bit history here. This is known as Gabriel's horn. This Gabriel's horn is maybe the shape in which already was studied by this Italian mathematician during 17th century, because the shape of this function looks like a horn. And then on Judgment Day, Gabriel certainly here blows into this like a horn to announce that the Judgment Day starts. Or sometimes, for example, some mathematician, they call it Painter's paradox. The reason for Painter's paradox is how can be possible you have got a finite volume of paint, but this finite volume of paint can cover infinite surface area. This is assumed that, for example, now you have got a surface area of a place, like maybe a house, maybe a home, in which the surface area is infinite. But you can buy maybe a small can of paint, but you can paint all of it. That's why this is named as a paradox. Now, another question here is, are there any other functions that have the same property? When we say the same property, it means they have got a finite area, an infinite, for example, surface area. The answer is yes. Obviously, there may be many, but probably we do not know what they are, those functions. But we can easily categorize them. For example, here what I did for the 2D function, this may be a group of functions in terms of n, obviously, means x to the power minus n. And in 3D, this is the function. And the reason for n greater than 1 and again greater than or equal to 1 is due to the fact of the integration, in which we have learned that if you integrate it, and if it's equal to 1, you cannot apply the normal rule. You'll have to use logarithm. So I'll just try to avoid that. Now, if, for example, I take a 2D shape, then assume that n is equal to greater than 1, because now easily you can see that if n is equal to 1, then it means the meaning of this integration is useless, because it doesn't make sense. How come this integration will become equal to infinite? That's why we start from n greater than 1. We do not assume n as negative. The reason is clear, because the shape of the function then becomes like this, in which all our discussion will not be valid, certainly. Then if I have got in terms of n, for instance here, if n is equal to maybe low value, and then gradually here, if you increase n, this function moves more towards here. And then you notice that the area between the function and here decreases. If this area depends on n, and if n becomes very large, then it means maybe this function perhaps looks like this, probably a very, very thin, tiny line going here, and then approaching 0. Then it means the area will become very small, or maybe even 0. But the perimeter still is infinite, because the perimeter, if you look at it here, does not depend on n. Still, regardless of this integration, still this is equal to infinite. Has nothing to do with this integration. Now, 3D. In the case of 3D, we have got similar methods in which we apply. The volume can be calculated, for example, in terms of n, although the value of the volume is slightly different, but it's fairly easy. But here, do not forget, n has to be greater than half in this case, because if you substitute half here, it will create a problem in which it is infinite. And the surface area is equal to infinite. So again, here, this function, if, for example, n increases, you notice that this function more or approaches more towards here, then it becomes more closer to 0 more quicker. Then if you work out the surface area in the same way as we had before, through, for example, expansion, then you can easily demonstrate that this is equal to infinite just because of this, by the way, not because of these ones. Because these ones, if you calculate them, almost they become either a simple constant or maybe a 0. But the main contribution for the infinity here is this part. So that's why whatever the value of n is, the surface area is infinite. But if, for example, now you go back to the same discussion as you had earlier on, if n becomes very large, you notice that the volume becomes very small. I think this can be probably imagined, because now the function will become very, very, very close to this. Then it produces or generates almost 0 volume, but infinite surface area. Now, the next step here is what are the limiting values? Although the limiting values are easy, because if this time here assume n approaches infinite, then it means my volume will become 0. But if I assume the same thing here as n approaches infinite, obviously here this is itself, regardless of n, independent on n, this is infinite. So it means simply the conclusion is If n becomes very large, volume becomes zero, but the surface area becomes infinite. So you have got an object. This is strange again. You have got an object in which it has got a zero volume, but infinite surface area. The surface area can cover the entire of this universe. Okay. Another function. This is another function here. This is just to practice, by the way, here, and then to make a bit more understanding on this topic here. For example, this is a different function, and the shape of this function looks like this, certainly. Okay. Then if you calculate the volume will come out to be equal to pi over 4. And if you work out the surface area, this integration, again, here we have got problems. This may not be very easily solved analytically. As far as I'm aware, I haven't seen any analytical solution for that. But at least for the purpose of this analysis here, because we have got infinity, sometimes these integrations, if you expand them, the calculation may be a bit easier. Then we reach to a similar conclusion that this integration, can you see the integration of this, the integration of 1, which is constant, is equal to x practically. Then certainly at this end is infinite, then this is infinity, regardless of this part. So even if you don't calculate this, it doesn't matter. So we don't need to worry about that. So it means this integration comes out to be infinite. So this is another type of function in which is producing finite volume and infinite surface area. Maybe, for example, I can leave it for yourself as exercises. If I have got x to power n e to power minus x as a function, then we can study here in depth here how the behavior of this infinity changes with the value of n. Okay. The next step here is, another interesting point is, for example, let us say we assume that not extending to infinity, extending to some point, but given that the area is 90% of the original one, okay? Maybe this 90%, I assume it, you can assume 95, you can assume 90, you can assume 85, whatever. Then you notice that the value of this A here comes out to be 10, and then the area will become finite, and the perimeter will become finite. Then it means the conclusion is easy. Note that infinite perimeter of the shape boundary here only happens when the area is maximum. This is an interesting point. So it means it cannot happen always. It happens when the area is maximum. Similar argument can be applied obviously here to volume. Okay, in the case of volume, you can do very similar thing, and you can reach to the same conclusion. So it means infinite surface area of these functions here can only happen when the volume is maximum. Cannot happen, for example, at elsewhere, where the volume is different. Now, finally here, this is the final step. I'm not producing a conclusion here, but just few little comments may be useful. Usually, any shape spans two of its properties in two different dimensions. For example, n and n plus 1. Like, if I have got an ellipsoid, this ellipsoid is just an example, its volume is defined within 3D, but its surface area is defined within 2D. This is very common, basic of geometry. And if I take a polygon here in plane geometry, its area is defined in 2D, but its perimeter is in 1D. But a line, the line has got a length, this is the property, in which is defined in 1D, and the endpoints are 0D. But now the question is, which is supposed to be for a different video here, what is the case if, for example, I have got, let us say, a 4D or maybe even 5D shapes? Then in those cases here, we need to introduce complex or complicated integrations here, defining hypersurfaces and hypervolume to justify the others, and hopefully this will be in another video. Any comments, any points in which you have, please, you can email me to that, and thanks for the watching.